So let us specify the chemical period
Hmm.
the element. Ensure that when you join in, you uh, talking to us. Sheila, Sheila,
What is speaking?
please can
Even balance is
Sheila,
what have I done again?
let us mute.
They used to pay, they stopped paying. They used to pay me. You don't come- I'm not
Sheila, mute. Okay. All right. Thank you so much. You want to unmute? And you want to speak to us? All right. Let us start demystifying this chemistry of period 3 elements. Now, under this topic, we are going to look at the following. We are first of all going to see the elements in period 3, and we describe the various physical properties of those elements. When you speak about physical properties, here you should note to speak about the melting points, the boiling points, ionization energies, atomic and ionic radii, electronic structures, uh, the electron affinity, electronegativity, positivity, electrode potential, and electrical conductivity. Also, we are going to describe the chemical reactions. You'll see the chemical reactions of these elements, the reactions with the air, reaction with the water, acid, alkalis, nanometals like chlorine, carbon, sulfur, and others. In this topic, we shall also discuss the elements, the compounds of these elements. Majorly, the emphasis will be on the oxides, the ozo acids, the chlorides, and the hydrides. Their physical properties, chemical properties. If time allows us, we shall demystify all these in this topic. But not in this lesson, we may take some good lessons. So we shall also look at the qualitative analysis and the lastly industrial processes and chemistry of aluminium. Yes, let us start with the first objective, that's the element. Let's see the elements in period 3. I hope you are still together. Can a person to give me a response? Maybe speaking here when the network is off. Hello? Someone to give us, someone to unmute and, okay. D, there is someone called D. Hello? Someone to unmute. Someone to unmute. I have actually enable delay setting. Someone to unmute and a response.
So we listen.
Okay, great. Now let us try to see the elements. So before I display the elements that are in period 3, someone to give me some of the methods that we are having in period 3. Hello? Someone to give me the methods that we are having in period 3. Anyone? You can unmute and speak to us. I have enabled the settings for you to unmute yourself. Hello? Okay, let me display them. Okay, Kusima raised up a hand. You can speak to us. You can speak to us. Kusima, you raised up your hand and unmute yourself and speak to us. There is Rona. Rona, you can also speak to us. Yes, Rona. Hello. Yes, Rona. Rona. All right. Let me display them. Yes, this is the table that I've tried to summarize for us. The elements in period 3, various symbols, the structure, type of bonding, electronic configuration using the atomic numbers. So these elements, I know you know most of them. You've ever seen the symbols. We studied these symbols in O level. Now, my major emphasis is on the structure and the type of bonding. Electronic structure configurations, I know were introduced to you. My emphasis is on the structure. This structure, they are always asked. You find them, there are very many questions in the question bank asked. They can give you the element like sodium, ask you the structure, also in paper 1, and the type of bonding. So the reason why I choose the methods that we are having in period 3, wanted us to know that all these metals, that is sodium, magnesium, aluminum, period 3, have metallic bonds in them. The atoms in these metals are joined by metallic bonds, and they form what we call giant metallic structure. I want us to look at the giant metallic structure. Let us look at this peak. As it is loading, can I get a response from you? Are we still on? Hello? Hello? Are we still on? So this is the giant metallic structure. This is the giant metallic structure in 3 dimensions. Where you see this one in green may be the atomic, we can call it the cation, maybe the cation, and this is the electron. The giant metallic structure is formed by the interactions or the attractions between the atoms and their electrons. So you can find that this is the giant metallic structure in 3 dimensions. You can still look at another one. Another kind of giant metallic structure formed, though this one is more in 2 dimensions. This is the metal ion, the positive one, the nucleus, positively charged nucleus. This is the electron as described here. So very many atoms come up together to form the element. Let me help you distinguish between an element and an atom or a molecule. An atom is invisible. You can't see an atom, but you can see an element. When you look at the iron sheets there, the rental or in the house or in the bungalow you are in right now, that's an element, the iron sheet or the iron sheets. When you look at a nail, iron nail, that's an element. You can see it. But an atom is invisible. You can't see it. The same thing with a molecule. Molecule is invisible. A compound is visible. So an element is made up of very many atoms. Now, an element may be of sodium, which you can see, or an element of aluminium, like now the saucepan you use to prepare meals. That's an element of aluminium. That element is composed of very many atoms. Now, those atoms are arranged in this format. They are arranged in such a way that there is a positively charged nuclei and the other energy levels, which is here, this one here. You can say this is the positively charged, this one, the positively charged nuclei and other energy levels. And then this is the electron. You see, metals bond, metal atoms bond with others by giving out electrons, such that they form electrostatic forces of attraction between the positive nuclei of the metal atom and the delocalized electrons. So this one is the positive nuclei, or which we can call the metal ion, and this the delocalized electron. So they give out electrons and then form metallic bonds. So we can say that metallic bonds are formed by an interaction, which is we call an electrostatic force of attraction between the positive nuclei of the metal atom and the delocalized electron, or we can call it between the metal ion and the delocalized electron. So these are metallic structures. This is the metallic structure in 2 dimensions. The metallic structure in 2 dimensions. So it's in the form of this. It's very big, though here for classwork we can put it in that arrangement. Okay, so let us try to look at now other structures. You can see now metals, all the metals in period 3, the structure is giant metallic. And the type of bonding is metallic bonding, or the type of bond is metallic bond. I know you know how to write the electronic configurations. If there's anyone who is not well versed with it, we can still densify it. You can just raise up the hand and you see a way of doing it. All right, you can still chat. Oh, someone has said that, teacher, I'm not seeing the images. Okay. Let me try to share again. Let me hope you are seeing the images now. Let me hope we are seeing the images now. You can chat with me. Let me hope we are seeing the images. All right, so I was trying to emphasize this. No, still. Oh, yeah. Screen. Hope you are seeing the images now. Hello. Hope you are seeing the images. Okay, great, great, great. Yeah, so now, this is what I was showing you. Or this is what I want to show you. So, giant metallic structures are like this. This spotlight that you are seeing here, the red icon that you are seeing here, this one may be the positive nucleus and the other energy levels of the atom, which we can call the metal cation. And this one may be the electron. So metals, atoms in the metals bond through metallic bonds. The metallic bonds are just electrostatic forces of attraction between the positive nuclei of the metal atom and the delocalized electron. So this can be the positive nuclei. The nuclei is positive. The electron is negatively charged. So this can be the positive nuclei of the atom, which we can call as metal cation. This one can be the electron. So metals bond through delocalizing their electrons, more so the outermost electrons. So when the outermost electrons are delocalized, they again form electrostatic forces of attraction between those delocalized electrons and the positive nuclei of the metal atoms, so that they can form that bond. So the giant metallic structure can be of this kind. It is giant, very big, and it can lead to formation of solids. So very many atoms come out together to form an element. As I've told you that when you look at those iron sheets, that's an element. You can see it with your eyes. Or when you look at the iron nail, the iron bars, that's an element of iron. When you look at the saucepan, that's an element of aluminium. So that element of aluminium is composed of very many metals in this form, very many metal atoms in this form, having what we call a giant metallic structure. So that's the giant metallic structure. In 2-dimension, we had it in 2-dimension here. Add it in 2-dimension so that you can see. So this is the 2-dimension part of it. This is the metal ion, and this is the negatively charged electron, the delocalized electron. So this one we can call it the positive nuclei of the metal atom, and this one is the electron. This one, let me put some spotlight. This outer one here can be energy levels here. In the center, this is the nucleus. This one is the electron. So this attraction here, you know, something that involves positive and negative, we call it electrostatic. So this is an electrostatic force of attraction between the delocalized electrons and these electrons. The delocalized electrons are always from the outermost energy level. So between the delocalized electrons from the outermost energy level and the positively charged nucleus of the metal atom. So very many atoms come up in this kind of arrangement to form an element. So these are what we call the giant metallic structures. When they speak about metals, the structure in metals, just know, is called the giant metallic structure. Yes, we are going to see how to describe them seriously. And the structures. Now, when we look at the silicon, silicon is a metalloid with a giant covalent structure. All structures that start with the giant, just know those structures lead to formation of solids, most of them. And those solids are always hard. You see, silicon is also hard and is a solid. at room temperature. Silicon is also hard. So it forms a giant covalent structure. Forms a giant covalent structure. The spelling is here. It would be metallic, giant metallic, but for this case, the type of bonding is covalent. So that's why we call it giant covalent. If the type of bonding was metallic, we would say giant metallic. But for silicon, the type of bonding is covalent. So it is a metalloid. Metalloids are those elements, or yeah, they are elements that can behave sometimes as metals, sometimes as non-metals. So silicon is one of them. The metalloid with a giant covalent structure. Some people call it giant atomic. Yes, it is okay. You can still chat with me. If you have any question, you raise it before I continue. Any question there? Any question? Anyone with a question? Okay, seems that you don't have questions. All right, so let us see the giant covalent structure of silicon in 3 dimensions. The silicon atoms arrange themselves in such a way that one atom of silicon is, or each atom of silicon is covalently bonded to 4 others in a tetrahedral arrangement, as you are going to see in this peak. Hope we can see the peak. Hello. Yes. Oh, someone is saying no. Some people are saying it already. Great. So in this peak, when you look at this, each corner, take it to be a silicon atom. Now like this. Let us take this one to be a silicon atom. If you look at it, hope you can see that spotlight where it is, that red. So if this is a silicon atom, it must be covalently bonded to 4 others. This is 1, 2, 3, 4 in a 3 dimension. So in 3 dimension, it is covalently bonded to 4 others in a tetrahedral arrangement. This is a tetrahedral arrangement. One is going the other side. The tetrahedral arrangement sometimes is drawn like this in your books. You draw it like this. So this one is drawn in 2 dimensions, but here we are looking at it in 3 dimensions. We are looking at it in 3 dimensions. So each silicon atom here is covalently bonded to 4 others in a tetrahedral arrangement. Even this one, there's another one that is shielded. You can't see it. It is the other side. It is hidden the other side. So even this one, when you look at this and try to count, there's 1, 2, 3, 4. Even this one will be joined to other 4, but in a tetrahedral arrangement. That is silicon. So it forms what we call a giant covalent. It is covalent because there is bonds here. These bonds here. Those bonds are covalent bonds. They are covalent bonds. So that's why we call it giant covalent. It is giant because it forms very strong solids. So you see, the structure you can easily tell it when you just get to remember that for silicon is very strong. Silicon element is very strong. So it forms giant, and the type of bonding is covalent. So when you combine the two, you come up with the structure as giant covalent. It's very extended. Very extended. All right. So that's the structure of silicon. It's giant covalent. When you're describing it, you just say, when you're describing the structure of silicon, just say silicon forms a giant covalent structure or giant atomic in a 3 dimension in which each atom is covalently bonded to 4 others in a tetrahedral arrangement. That's how you can describe it. All right, let us continue and see phosphorus, sulfur, and chlorine. Now, phosphorus, sulfur, and chlorine, phosphorus, sulfur, and chlorine are nanometals. And these nanometals are funny in such a way that for them, they form molecules. They first form molecules. Then after forming molecules, molecules combine to do what we call van der Waals forces of attractions. Hope someone has ever heard about van der Waals forces of attractions. Can get some messages here. Have you ever heard about van der Waals forces of attractions? Yes, someone has said yes. Oh, great, good, good. So they first form molecules. I've told you that molecules are invisible. Molecules and atoms are invisible. They can't be seen. But what you can see is an element or a compound. Now, these ones first form molecules. Then molecules can be composed of, now for phosphorus, one molecule of phosphorus is composed of 4 atoms. They combine and they form that molecule. One molecule of sulfur is composed of 8 atoms. So we can call it octatomic. One molecule of chlorine is composed of 2 atoms. You can call it diatomic. Argon is monatomic. Exists as one molecule. Argon is like these people who don't marry, no, are always single. So it is monatomic always, because it is a noble gas, an inert element, an inert gas. So after forming molecules, now the molecules come together to move and all forces of attractions. So the structures of those molecules, the structure of each molecule, now like for phosphorus, the structure of phosphorus can be drawn. The structure of sulfur can be drawn. The structure of chlorine molecule can be drawn. The structure of argon molecule can also be drawn. So those structures, the structures of those molecules can be drawn. Since they can be drawn, we call them simple molecules. Someone is telling me that teacher would consider silicon to be having tetrahedral since the other are diatomic. Not at all. Silicon has a giant covalent structure. That is the structure of silicon. It doesn't have a simple molecule. It doesn't have a simple molecule. So we cannot consider it to be having a tetrahedral structure. Silicon has a giant covalent structure because it is extended. It is an extended form. One combine the other with another and another until when it can form an element which you can see. So it's not a simple structure. Not at all. Okay. So let us continue. Phosphorus, sulfur, and chlorine are the ones that can form molecules. So if they can form molecules, they have simple molecular structures which we can even draw, as we are going to see them. Let us see them in 3 dimensions. So that is the structure of phosphorus. Can be easily drawn. Let us try to draw it here. The structure of phosphorus is always drawn in a 2 dimension like this. Very easy. So like that. Let me try to redraw it very well. So it can be easily drawn like this. Just as simple as that, where each corner is having phosphorus. Each corner is having phosphorus. So each corner is having phosphorus. Yes, someone said that it is a tetrahedral arrangement, not a structure. Yeah, the arrangement is tetrahedral, but the structure is giant covalent structure for silicon. Okay. So this is the structure of phosphorus molecule, one molecule of phosphorus. In the 2 dimension, 2 dimensions like this. 3 dimensions like this. 3 dimensions don't need it, just need to know. Just showing you. Just need the 2 dimensions. This is how we draw it. But it is derived from this. If you see this line, maybe this. You see this line here, this bond here, maybe this. Then this bond here is this one. This one is this bond. Then this bond is this. And lastly, this bond here is this one. So in 2 dimensions, we can just summarize it like this. Hope we are together. All right. So that's in 2 dimensions. That is phosphorus. You can see sulfur. Now this is sulfur. This structure is the same as the one that we draw even in 2 dimensions. You can just simply draw it like it is. As if you are drawing a W. Someone took my art. Don't know who stole my art. I'm trying to draw. Where each corner here is sulfur atom. So the same thing with this here. They are the same. So this is sulfur atom, so also sulfur atom. So this is 1 molecule of sulfur. 1 molecule of sulfur, which is octa-atomic. 1 molecule of sulfur is like that. Now these molecules, they will come up together through van der Waals forces of attraction to form an element of sulfur, which you can see. Sulfur majorly is found in underground. Underground, you can see it. You can get it for those who dig pit latrines. That is chlorine. That is chlorine, the diatomic. Chlorine is diatomic. This is 1 atom, and this is another atom. These peaks were generated using some technology, which is not covered at our level, but it's called spectroscopy. Okay, so now we can summarize this. When they ask you about the structure of the metals in period 3, any of the metals in period 3, just know the structure is giant metallic, and the type of bonding is metallic bonding. If it is silicon, the structure is giant covalent. That's the structure, but the atoms in the structure, each is covalently bonded to 4 others in a tetrahedral arrangement. All right. Now, if they ask about the nanometals, that is phosphorus, sulfur, and chlorine, just know the structure is simple molecular. simple molecular, because we can draw the molecular structure. So it is simple to draw simple molecular. And the type of bonding, these nanometals and the silicon is covalent. Yes. Any question? Hello. Do you have any question? Catherine, any question? Any question, Catherine? Okay. So let us continue. We have looked at the structures and type of bonding. Let us put them, we are going to see them in words and how we can describe them. That's some good introduction on the elements of period 3. Let us now look at the physical properties of these elements. And we shall start with the physical state. I'll start with the physical states. The physical properties of elements C, period 3. Let's start with the physical state. I know we have discussed most of these things in the above slide. We have been showing you pics. I know we know that sodium, magnesium, silicon. I know we know that sodium, magnesium, aluminum are metals, so they must be solid. Additionally, silicon form giant covalent structures, which can make it to exist as a solid. Also, phosphorus. Phosphorus also is a solid because of the profound van der Waals forces of attraction. Van der Waals forces of attraction are very many in it, all very strong. Even sulfur forms some strong van der Waals forces of attraction between the molecules, because the molecules have some higher molecular mass, very big molecular mass. So it makes it also to be a solid. Chlorine and argon, chlorine form weak, very weak van der Waals forces of attraction between the molecules due to very low molecular mass. So it makes it to be a gas. Argon is monatomic and also form the weakest structure in period 3 van der Waals forces of attraction between the argon molecules. So it is a gas. Now, this is the summary of the physical state. The period 3, you have sodium, magnesium, aluminum, silicon, phosphorus, sulfur are solid. And then chlorine and the argon are gases. Chlorine and argon are gases. Let us try to see how we can describe the structures of these elements. What can we write when you're describing the structures of these elements? I'm going to go through it, but it's the same thing that we have been discussing. First of all, when you're speaking about the metals, that is sodium, magnesium, aluminium. They ask you to describe the structure of the elements in period 3. The metals are generalized. They have the same structure. That's giant metallic. Sodium, magnesium, aluminium are metals. They have giant metallic structures. We saw the giant metallic structures. And in the giant metallic structures, each atom is held by, all the atoms are held by metallic structures. These metallic structures, these metallic structures are formed. These metallic structures are formed when the atoms form electrostatic forces of attraction between the positive nuclei and the delocalized electrons. But when you're describing simply, you can summarize and say sodium, magnesium, aluminium are metals with giant metallic structures, in which metals are held together by metallic bonds. Now for silicon, we said it is a metalloid. We said metalloids are the one that you can either sometimes behave as metals, sometimes behave as non-metals. So we say silicon is a metalloid with a giant covalent structure, or we can call it giant atomic structure. The structure of the atom, the arrangement of the atoms all together extend to a giant covalent structures. Giant covalent structure or giant atomic structure in 3 dimensions. But in that extended structure, each silicon atom is covalently bonded to 4 others in a tetrahedral arrangement. So when you just get 5 atoms of silicon, there must be arranged in a tetrahedral. But if you get silicon element, the whole element of silicon, it has a giant covalent structure in 3 dimensions, in which each silicon atom is covalently bonded for others in a tetrahedral arrangement. I don't know whether some people have ever seen silicon. No one has ever seen silicon. Yeah? Do you have some people who have ever seen silicon? Okay, so this is how we can describe it. So silicon is a metalloid with a giant covalent structure or giant atomic structure in 3 dimensions, as you saw it. 3 dimensions in which each silicon atom is covalently bonded for others in tetrahedral arrangement. Surely we saw it in a pic. Let me try to share it here. Surely we saw it in a pic. That pic there. If someone raised that hand.
Yes, teacher. I'm an econ
Yes.
student, and I'm an econ student, and I'm requesting the link to the econ lesson.
Sure, you can go in the group. You find it there.
I'm not in the group.
You need to contact with Mr. Kaziba.
Okay.
Okay. Okay, so this is the structure of silicon that we're describing that silicon is a metalloid, is a giant covalent structure. The whole of this extended thing here is the giant covalent structure. More atoms are there, but we try to capture only this in 3 dimensions. This is the 3 dimension in which each silicon atom is covalently bonded for others in a tetrahedral arrangement. You can see the tetrahedral from there, here. Let me show you. If you try to figure out the tetrahedral, this bond and this one, then connected to this, connected to this. One atom here is connected to 4 others in tetrahedral arrangement to form the whole of these atoms combine the same manner to form an extended structure, which we call the giant covalent structure. So that's how you can describe the structure of silicon. That's how we can describe the structure of silicon. So these others are nanometals like phosphorus, sulfur, chlorine. Then argon is a rare gas. Argon is a rare gas. So these ones, they have simple molecular structures. I told you the simple molecular structures are for the molecules. And after forming those molecules, the molecules now come up together to move under all forces of attraction, whose strength increases the increase in molecular mass. Yes, someone raised up their hand called Casal.
Thank you, Master. I'm requesting that you help us and we go back to the other screen where we're describing the structure of elements. Please.
The structure of what?
The screen, because for me I'm still seeing the image of the arrangement of silicon. So I'm requesting that if we are done, you help us and we share the recent screen.
Okay. Let me share. So hope you are seeing it. Yes. Yeah. So Christine, are you speaking nothing? Okay. So this is the structure of silicon. Any question there?
No.
Don't have questions? Okay, so this is the structure of silicon. And when you're describing it, we say silicon as an element. Silicon element has a giant covalent structure, or which we call the giant atomic structure in 3 dimensions, in which each silicon atom is covalently bonded, in which each silicon atom, now like this one here, is covalently bonded to 4 others. That's 1 bond, 2, 3, 4. 4 others in a tetrahedral arrangement. So our friend told me, asked me to kindly share the speak. I don't know what was the intention or what he wanted.
Maybe they've just been teaching evaluating
what-
participants.
What? Okay. So now maybe we can go to, we can continue. So we looked at the structure of silicon, the metals. Now let us look at the phosphorus, sulfur, and chlorine. Let's say when you're describing the structures, we say they have simple molecular structures in which molecules are held by weak van der Waals forces of attraction, whose strength increase with increase in molecular mass. Now when you look at these ones, look at the structures. Let's try to look at the structures of phosphorus. Sulfur, that's the structure of sulfur. When you look at the structure of phosphorus, the structure of sulfur, there are 8 atoms. When you look at the structure of phosphorus, there are 4 atoms. Molecule.
Mark.
The structure of chlorine, there are 2 atoms in each molecule. That one of argon.
Who is Mark?
1 atom.
Wait, what?
Hello.
What?
Hello. Okay. So these are the one here in a 2 dimension. This is the structure of silicon. It is extended, so it is giant covalent. This is the structure of phosphorus. The structure of phosphorus, there are 4 phosphorus atoms in each phosphorus molecule. This is 1 molecule of phosphorus. This is 1 molecule of sulfur. This is 1 molecule of chlorine. Sulfur, when you look at it, there are 80 atoms in 1 molecule. So the molecule of phosphorus, sulfur, chlorine, argon are, phosphorus is tetraatomic. sulfur is octatomic, chlorine is diatomic, and the argon is monatomic. Now we said that phosphorus, sulfur, chlorine, and argon have simple molecular structures in which the molecules are held by van der Waals forces of attraction, with strength increase with increase in molecular mass. When you look at the molecule of phosphorus, it has 4 atoms. Try to calculate the molecular mass of phosphorus. To try to calculate the molecular mass of phosphorus. Molecular mass of phosphorus. Which answer are you getting? Phosphorus molecule. Which answer are we getting when we try to calculate the molecular mass of phosphorus molecule? Hello, someone can type it in the chat. I can see it, or you can unmute and speak. Hello. Yes, someone has gotten 256. Thank you, Faith. When you try to calculate the molecular mass of sulfur molecules. Sulfur molecule. Which answer are we getting there? Hello, someone can type it in the chat to be able to see it here. Which answer are we getting? Molecular mass of sulfur molecule. Sulfur molecule has 80 atoms. We want to see which one will be having a higher strength for the van der Waals forces of attraction. Because I said that they have simple molecules in which molecules are held by van der Waals forces of attraction whose strength increase with increase in molecular mass. So we want to see which one has a higher or the highest strength for the van der Waals forces of attraction, followed by which one, like that. So we have seen that if phosphorus has a molecular mass, phosphorus molecule has a molecular mass of 256. Then the molecular mass for sulfur molecule is, someone type it in the chat. Hello. Can I get a response? So each atom of sulfur is 32, then times 8. Okay. So it is 256. Then that of phosphorus is 124. Then that one of chlorine molecule. The molecular mass of one chlorine molecule. Chlorine, each chlorine atom is, yes. Okay. Thank you, Miriam. Then argon is monatomic. So argon is monatomic. One argon molecule will be equal to, and type it in the chat. Yes. I said for sulfur, the molecular mass of the molecule is 256. Mass is 71. Argon, the molecular mass is 40. So after getting to know their molecular masses, we can now determine which one has the highest strength of van der Waals forces of attraction, depending on the molecular mass. Because we said that these structures formed, the molecules are held by van der Waals forces of attraction, whose strength increases in molecular mass. So from the chart, let me get the response from the chart. Which one will be having the highest magnitude or strength of van der Waals forces of attraction, depending on the molecular masses here. Which one will be having? Hello. The sulfur molecule. So sulfur as an element is the one with the highest among the nanometals and the rare gas, that is argon. Yes? Because we have phosphorus, sulfur, chlorine, and argon. Among phosphorus, sulfur, and argon, sulfur is the one with the highest magnitude or strength of the van der Waals forces of attraction, because it has the highest molecular mass among phosphorus, sulfur, and chlorine and the argon. Then followed by followed by phosphorus, then chlorine, and lastly argon, according to the values of the molecular masses. Look at them here. All right. Thank you so much. Now let us see how we can use the above information described using deriving the trend in melting point. All the above that we have discussed is going to help us. The structure, more so the structure, this structure here. Hello. You can type in the chat. Are we still together? Don't know whether my network has jammed or we are still together. Hello, friends. Are you getting me? Hello.
We are getting you, sir.
Oh, good, good, good. All right. So let us continue. This is a question that I want us to discuss and to mark the end of our today's discussion. So friends, this kind of a question was set in UNEB 2016, paper 2, number 7. And when you also check in UNEB 2007, paper 2, number 2, and the UNEB 2000, paper 2, number 5, you find the same kind of question. So it has appeared 3 times in UNEB. So don't say that here things are not set, they are set. So seriously, the table having different melting points and atomic numbers of the elements in period 3. They want us to describe the shape of the graph after plotting melting points against the atomic numbers. Now, when you are describing the melting points, of the elements in period 3. The elements in period 3, we have a group of metals, we have the metalloid, we have nanometals together with the rare gas. You have to describe the metals differently or independently, metalloid independently, then nanometals and rare gas, you can also describe them, can group them and describe them independently. So when I'm describing such a question, it has a minimum of 6 marks. You have to put all the marking points. When you're describing the melting points and boiling points of period 3 elements, we describe them basing from their structures and the forces of attraction between either the atoms or the molecules. In metals, we talk about the forces of attractions in atoms, between atoms and the electrons. Silicon, the forces of attraction are between atoms and atoms, so between atoms actually only. Phosphorus, the forces of attraction are intermolecular. Phosphorus, sulfur, chlorine, and argon. These 4 here, the last 4, the forces of attraction are intermolecular, and we call them van der Waals forces of attraction. And their strength depends on the molecular mass. I tried to draw this graph in my PowerPoint here. I try to display it. But even from the data given here, you can see that it's increasing up to here, up to silicon, then decreases. But this decrease had some abnormalities where sulfur is having a higher melting point than phosphorus. And also here it is increasing. Mute. Okay. So I tried to plot this. There are the plot, but I know you also have it there. This is the graph that I tried to plot using the other data, and the plotting may a new format. When you try to look at this graph, sodium, magnesium, aluminum, up to silicon, the melting point is increasing, but between magnesium and aluminum, the melting point is almost the same. Increases slightly. There's a reason. Then from silicon, the melting point is decreasing, but with an abnormality of sulfur having higher than phosphorus. That's the general trend that you can state. So the melting point increases from sodium to silicon, and then decreases from silicon to argon, with the sulfur having a higher melting point than phosphorus. That's the general trend you can state. It can earn you 1 mark or 1.5. So it increases from sodium to silicon, and then decreases to argon, with the sulfur having the higher melting point than phosphorus. Then you start describing. When you're describing, you describe the metals alone. Describe from sodium to aluminium alone. Describe, because these ones have the same, these ones have the same structure. This one has its own structure. And also these ones have the same structure. So we describe based on the structure. The structure here in metals covalent metallic. The structure here of silicon is called giant atomic, or you can call it giant covalent. The structure in these ones is a simple molecule. Simple molecule. So we use structures to when you are describing the trends in melting points and boiling points of periodic elements. So you are going to describe this one independently, this one independently, and this one independently also. So we say that sodium, magnesium, aluminum are metals with giant metallic structure. Now you describe how the giant metallic structure is arranged. You say, in which atoms are held by strong metallic bonds. Now these metallic bonds, their strength depends on the number of electrons contributed per atom towards the metallic bond formation, and also the strength of metallic bonds also depends on the atomic size. There are two factors that affect the strength of the metallic bond. So we based on two things. You have to know the structure and the type of bonding. Here it is metallic. Or the type of bonds that exist. Here it is a metallic bond. Here is still covalent. And also here is covalent, but the covalent is here it is more extended than here. Someone speak to us. Vivian, can you mute if you? Yes. Okay, thank you. Oh, So you need to know the structures and the type of bonding and their arrangement. Then after knowing the type of bond, to know factors affecting the strength of that bond. Now, like for metals, they have their antimetallic structures in which atoms are held by strong metallic bonds whose strength increase with decrease in atomic radius and increase with increase in number of electrons contributed per atom towards the metallic bond formation. So that's why we see that the atomic radius, we are going to see it under the trends in atomic radius. But we know it that atomic radius or the atomic radii decrease across a period. So we know that from sodium to aluminium, we are describing under metals. The atomic radius or the atomic radii decrease. And we have said that the strength of metallic bonds increase with the decrease in atomic radius. So it means that the strength increases. And also, from sodium to aluminium, the number of electrons contributed per atom towards the metallic bond formation increases. So that's why we are seeing that the melting point also increases. But the melting point, there's an anomaly. There's no sharp increase between magnesium and aluminium because aluminium, instead of contributing 3 electrons towards the metallic bond formation, contributes 2. These metals, when they are contributing electrons towards metallic bond formation, they contribute the outermost electrons. The outermost electrons in aluminium are 3, but it contributes 2 instead of contributing 3. So that affects it and decreases the melting point to almost be equal to that of magnesium. Let me try to share. Let me try to share the literature. You, Namtevi Patricia, you can mute. Namtevi Patricia, you can mute
Sorry.
for us.
Hello.
If you are not speaking, please mute. Or if you have any submission, you can put it forward.
Okay,
Or
please.
any question.
Okay, but I've just joined right now, so I'm still following.
Okay. Tap on the microphone because the background noise is polluting our class seriously.
Oh, okay. I'm sorry.
All right. Thank you. Tap on that microphone, then it will mute.
Okay.
All right. So let us see the literature. So this is what I was telling you when I described the trend. You have to describe the general trend. Let us that the melting point increases as we've seen. As we've seen, it increases from sodium to silicon, then decreases from silicon to argon, with sulfur having a higher melting point than phosphorus. So that's what we need to describe here. Melting point. That's a trend. And you 1 mark. or 1.5. Then we need also to describe them independently. Metals, silicon, which is a metalloid, and then nanometals. As I've told you here, that we describe these ones independently, silicon independently, and also these ones here independently. You have to know the structure in the describe them. You know the type of bonding and the factors that affect that, the bonds, or the type of bond, and the factors that affect the strength of the bonds in these metals. Also to describe that of silicon, the melting point. This is general for melting points and boiling points. You have to know the structure, type of bonding, and the arrangement. Then to describe the variation in nanometers and this area, guys, you have also to know the structure, which is simple molecular structure, type of bond, in the type of bonding between the molecules and the type of bonding between molecules, the factors that affect the strength of the and also to the molecules. Samuel, and Veronica. Samuel and Veronica, please can you mute? Samuel. Okay, thank you. So you have to know the type of bonding or the type of interaction between the molecules, which is the Van der Waals process of attraction between the molecules. And whose magnitude depends on the molecular mass. Increasing in molecular mass increases the strength of the Van der Waals process of attraction. All right. So let us see the picture now. This is what we have been describing under the structures. So that's why I started with the structures and tried to take a lot of time there because I wanted us to look at it here and melting points when we are well versed. So this description is similar to that of boiling points of period 3. So that's the general trend, and this is how we describe that of what? Metals. So we say, I told you have to know the structure. So metals have giant metallic structure. Type of bond, strong bond. Then the factors that affect the strength of the bond. Metallic bonds decrease with the increase with the decrease in atomic radius, and also increase with increase in number of electrons contributed per atom towards metallic bond formation. Now, from sodium to aluminum, atomic radius decreases. We said here that the strength increase will decrease in atomic radius and increase in number of electrons contributed per atom towards metallic bond formation. And here we are seeing that from sodium to aluminum, the atomic radius is decreasing. Means that it is increasing the strength of metallic bond. And also we are seeing that the number of electrons contributed per atom towards metallic bond formation from sodium to aluminum is increasing. Still it is increasing the strength of metallic bond. So that's why we are seeing that from sodium to aluminum and the metals of period 3, the melting point is increasing. We said when I describe metals, silicon, and nanometals. We describe them independently because they have different structures. We describe based on the structures. Now let us see that of the anomaly. The anomaly that's there is aluminum is certainly having a higher melting point than that of magnesium. I already talked about this. Though aluminum has a smaller atomic radius than magnesium, it contributes only 2 instead of 3 towards metallic bond formation, making it having a slightly higher melting point than that of magnesium. Let us see that of silicon. We derive all these from their structures. That's why we first look at the structures. When I'm describing that of silicon, you need to know the structure of silicon. Silicon, we know that it has a giant covalent structure in 3 dimensions, in which the silicon atoms covalent, each atom is covalently bonded to 4 others, forming very many strong covalent bonds which require much energy. That's why it has the highest melting point among the period 3 elements, because of the extensive very many and strong covalent bonds formed when each atom is covalently bonded to 4 others in a tetrahedral arrangement. Yes. Now the other elements, the nanometals, that is phosphorus, sulfur, chlorine, and argon, we describe them based on their simple molecular structure. So they form molecules. So they have simple molecular structures in which molecules are held by weak van der Waals forces of attraction, whose strength depends on the molecular mass. So we say whose strength increases with increase in molecular mass. Increase in molecular mass. So we saw the structure of phosphorus is tetraatomic phosphorus molecule. We saw the structure. We also saw the structure of sulfur is octatomic. We also saw the structure of chlorine diatomic. And we determined the molecular masses of those different molecules. We saw that sulfur has the highest molecular mass, followed by phosphorus, chlorine, that's the argon. Therefore, that's why we saw that the melting point is decreasing from phosphorus to argon, with sulfur having a higher melting point than phosphorus. Sulfur has a higher melting point than phosphorus because it has a higher molecular mass than phosphorus, hence high strength or higher strength of van der Waals forces of attraction than phosphorus. So That's basically the description of this. So the first plasmon is the atomic sulfur is atomic, fluorine is diatomic, and when therefore the molecular masses and melting points increase from phosphorus to sulfur, then you reduce to argon. You get all your marks. The melting point of period 3, the variation and that's what we had for today. Thank you for participating. I'll see you in the next discussion.
Excuse me, teacher.
Anytime. Yes, we excuse.
Yeah, thank you, teacher. But I'm having some question here.
Yes.
This
What?
this is your name. Last year's your name, paper 1, number 7. It's about the melting points of those group period 3 elements, but these are chlorides from sodium to silicon. But I'm seeing the trend is decreasing, yet it is supposed, the melting point is supposed to be increasing.
Surely that you didn't ask about elements. The way they're asking about the elements.
They were asked. They asked. They asked. Why?
Of period 3.
Yes, chlorides of period 3.
Yes. Now, for us here, we're discussing about elements of period 3. We are going to see. We are going to look at the variation in the melting points of chlorides of period 3 or elements of period 3. But it's also simple. This one needed some general knowledge, needed just to know the structures also.
Okay.
When you're describing when you're describing the boiling point or melting point, here they ask the boiling point.
Yes.
Now, number 7, last year. Just needed also to know the structure.
Mm.
Yes, needed to know the structure. Describing melting points and boiling points of period 3, need to know the structure. They ask about sodium chloride, magnesium chloride, aluminum chloride. Sodium chloride and magnesium chloride, those ones they have the ionic structure. Actually, those ones, the structures are formed by attraction between ions. That is sodium chloride, that is sodium ion, and the chloride ion, forming giant ionic structures. Sodium and sodium chloride and magnesium chloride, then they have giant ionic structures. The ions are held by strong electrostatic processes, which the ions are held by ionic bonds, which require very, very high energy for the molecules to boil, or for sodium chloride and magnesium to boil, magnesium chloride to boil. These were chlorides of elements of period 3 that they asked. We're not asking elements. The description here that I've been sharing is for elements of period 3. But still, it's the same knowledge. Now, for aluminium chloride, you needed to know that it has a simple structure. Because it is a dimer here. They gave us a dimer here. That's a simple structure. And also silicon chloride. Silicon chloride also has a simple structure. So those two, they are actually, the magnitude in the forces of attraction between the molecules depend on the molecular mass.
Okay, thank you.
So this dimerized aluminum chloride has a simple structure. And also silicon tetrachloride has a simple structure. So we will say aluminum chloride and silicon tetrachloride have simple structures in which the molecules are held by weak van der Waals forces of attraction, whose magnitude depends, or whose strength depends on the molecular
mass.
yes, or increase with increase in molecular masses. Now this aluminum chloride becomes, it's predominantly covalent. Yes, it is predominantly covalent, so it is not ionic. That's why it doesn't have giant ionic structures, but has simple ionic structures. It has a simple molecular structure. So that was the question. Just needed you to know the structures of bond that is there and factors that affect that bond, that type of bonding, or if they are forming simple molecular structures. Just all these structures are held by forces of attraction, and the strength increases with increasing molecular mass. So here in this question of UNEP 2007, we see aluminum chloride. If you try to calculate the molecular mass of aluminum chloride that was given here, dimer here, it is higher than that of silicon tetrachloride. Therefore, aluminum chloride will be having a higher boiling point than the silicon tetrachloride. The trend took 1 mark, and someone would not say across period, someone should say the boiling points decrease from sodium chloride to silicon tetrachloride, because these are elements, these are compounds of the elements, or these are chlorides of the elements. We are going to look at the chlorides of period B. I put all the description or what we need to cover in this first slide. That's where all what we need to cover. So this is what we need to cover. We have today looked at the elements, variation in the physical properties. Our major emphasis was on the melting points, which are similar to the boiling points. So someone can look for questions that are about boiling points, because they are the same things. I'm going to share this work in the group, or Mr. Kazuto is going to share it. And you can read where you haven't gotten, and you can still ask questions. All right. I think That's all for today. Yes, you're welcome. Let us meet in another discussion, which will be communicated. Encourage your friends to engage in this online discussion because they are free and convenient. You can sit at home and enjoy the discussion. And always
Okay.
share. All
Okay.
right.
Bye.
All right. Night. Bye bye.
Bye. Bye. Bye. Bye. Bye.